Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are five modules. Now we'll be going adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept. And if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more. Thank you. Physics as a part of the physics 1 course. This is going to be our 30th lecture. So far, we have discussed a lot about the variety of materials, particularly in the chapter of crystallography, which tells you how solids are made of. Solids are made of by periodic arrangement of atoms and molecules. If you do not keep any atom or molecule, then that is just geometric points, that is called lattice point. They are repeated after a definite gap called lattice constant. The basic unit, the elementary unit is the smallest unit, rather you can think over, is called unit cell. Unit cell when repeated makes the full solid in three dimension. Unit cell can be of various types, because each unit cell is divided by three length element and three angles. So combinations. So the combination of, as I'm telling you, the unit cell is depending on the three variables, three length vectors, ABCs, and three angles, alpha, beta, gamma. Variety of combination of ABC and alpha, beta, gamma is going to give you the variety of unit cells. There are altogether seven basic unit cells, and how well you place the atoms and molecules there, that gives you 14 gravities. Ultimately, that makes all the solids. For example, iron is face-centered cubic, copper is body-centered cubic. There is another called structures are called hexagonal close packed. The quartz crystal, they are actually hexagonal the hexagonal structure. So there are a lot of examples, variety of example are there actually. Like iron, okay, is a gold actually. Iron is FCC crystal, as I mentioned. Gold is also FCC crystal. So variety of crystallographic structures are present amongst the materials we witness. Now in past day, actually last day, actually we put all our attention, all our focus on a specific kind of solid material, which are called semiconductors. So what I did the other day, I actually divided the material again into some categories, but based on the electrical conductivity. The one which makes very good conduction of electricity and heat, they are obviously metals, which are poor conductors of electricity and heat, they are called insulators, and which does not help, which is intermediate between metals and insulator, as you know, they are called semiconductors. And the semiconductor is the key of this modern physics. Semiconductor electronics is the heart of all the electronic devices we are using. So basically, knowing semiconductor, the physics of semiconductor, what happens inside a semiconductor, how to manipulate the electron flow through a semiconductor, all these things actually a major part of the electronic devices that we have got in on the electronics front that we have to address on. So physics of how you explain the electron motion, hole motion, all these things actually are key of explaining many devices which. So which are the semiconductors are essentially the key of many devices that we see in our daily life examples. Okay, so physics of semiconductor is the key of learning modern physics. And if you look at the flow of our course also, we spend a lot of time in knowing quantum mechanics, which actually are quantum theory to be fair. Next year we'll also learn a bit about that. So what all these things does is you apply these ideas for the purpose of explaining electron flow inside a semiconductor, how electron moves, how hole moves. So they become the quantum mechanics problem. So basically, semiconductor physics is the area of application of your quantum ideas. What happens in a semiconductor material, to know them, to explain them, is the key of this class. So the major objective of this lecture is that by undergoing this class, you will be able to explain variety of semiconductor devices, junction diodes, which some of you already know possibly. We'll again explain that how the electron flows through that or holes flows through that device, what is the amount of current you can get in that system. So all these things I should focus upon. Okay, and so at the end of the by attending the class, obviously the main outcome is that you'll be able to explain the physics of various popular semiconductor devices like the rectifier diode, like junction diode, Zener diode, rather, all these things. Okay, so let us explain it. This is something some of you know, have some priori knowledge also, but try to realize it. Some put a lot of focus. I'll try to put a lot of animation, pictures, what happens inside a diode, all these things. Our viewpoint will be a classical viewpoint. There is electrons or charged particle. They will move under some voltage, electric field. All these ideas we actually use for the purpose of the class. So let us do it. So this is the 30th class. This is me. You can always contact me in these numbers. And this is how we are defining the material. Okay, based on the conductivity, the materials may be metal, insulator, and semiconductor. Metals are the best conductors, you know. And we are now talking about semiconductor. Semiconductor will be extrinsic and semiconductor will be intrinsic. So that is something I told you last day. Normally in this discussion, actually by semiconductor we will actually mean germanium silicon, the group 4 semiconductor in the periodic table, uh, as a semiconductor of concern. Okay, and these are essentially intrinsic semiconductor, and so that means the conductivity is somewhere between metal and insulator at a relatively higher temperature. Okay, if we use band theory, you get some electrons in the conduction band. Okay, if you go beyond room temperature or so. So basically, that's why it is a very good example of semiconductor. If electron moves from valence to conduction band, then holes are created. In an intrinsic semiconductor, the electron and hole concentration are same. And the other part of the story is that dope semiconductor. That means you add more electrons into the system. That is called N-type doping. Hole, you add more absence of electron or holes in the system. That is the P-type doping. So this is something we discussed. This is the structure of an intrinsic semiconductor. In my previous video lecture, I tried to tell you how through the sharing of electrons amongst the silicon atoms, okay, you create, okay, this covalent bonding. Okay, you can see germanium, silicon, okay, all are shown, all are popular semiconductors. Okay, so through covalent bonding, okay, normally In intrinsic case, electrons are shared. Okay, but this is a band structure. Okay, the idea is that, as I mentioned, an absolute zero, this is filled in and this is empty. But if you cross the nuclear high temperature, gap energy, this energy, minimum energy you need to take an electron from here to there. And most of the in semiconductors like silicon, germanium, this is you can get it by application of this thermal energy using this Einstein's formula Kt. K is Boltzmann constant, value is like 8.6 10 to the power minus 5 electron volt. So that means if you apply say 500 Kelvin temperature here, okay, so that means if you put the value 8.6 10 to the power minus 5 multiplied by 500, that much of electron volt energy you are actually giving to an electron here. With that energy, this electron will move up. So if electron reaches here, so what it creates an absence of electron here, which is called a hole. So it depends on the concentration of the or the amount of. Actually, the idea is that each electron will move from here to there. So that means the moment one electron is created, one absence of electron or a hole is also in case of intrinsic semiconductor. So electron concentration and hole concentration are equal. So that's the Fermi level, which tells you how much electrons are present inside the metal, lives in between the valence band and conduction bands. Okay. So this is a story of intrinsic semiconductor, and you possibly be knowing how it changes in case of extrinsic semiconductor. Okay, I'll show you. Okay, how create extrinsic semiconductor through doping. For making n-type doping, that means you have to produce more electron into the system. You add a pentavalent element like that. So that arsenic and phosphorus, okay, they are 5 valent. See, the fifth electron is excess. Okay, so these becomes a free electron. Okay, this is free. This is free to do anything. So this electron has the license to do everything. Okay, so it will move randomly. It will add to the current, and more and more replacement you do, more and more substitution of silicon with phosphorus you do, more and more electrons you produce. So and these electrons will move, and a lot of current you'll be getting. Okay, into the system. Similarly, for p-type doping, you need absence of electron. So you add aluminium or gallium. Aluminum is trivalent. Okay, and you can see this is the absence of electron or hole. So one electron, what would happen? Nature does not allow this. So what would happen? One electron from here will try to go there. So hole will be now created here. Now nature does not allow this also. Maybe one electron might from here will go here and the hole comes here. So ultimately a hole flow is created. And the amount of hole you create is equal to the what would happen? The amount of substitution you do. Each germanium replacement is aluminium will create one hole. Okay, so ultimately more substitution means higher number of holes. So hole concentration will be more, and you'll get a lot of current in the system. So in a p-type semiconductor, hole becomes majority carrier. In n-type semiconductor, electrons become the majority carrier. Okay. So this is all about it, p and n-type semiconductors. And you can see this picture, majority is the electron is a minority in case of p side, and electrons, holes are the majority, and vice versa. In n-type, electrons are the majority, holes are the minority. Okay. Drift velocity, diffusion. As you know, it is the drift velocity with velocity of the particle under voltage. Electric field, or whatever it is, diffusion is the flow due to the due to the change in concentration. This is junction diode, and you can see the moment you join it, okay, you create a You see electron holes recombines and the depletion region is created. Now I want to show you something now with respect of this concentration of depletion region in terms of Fermi energy level. And we just see, realize it is so easy, so smooth. Okay. Now suppose I choose one N-type semiconductor. Okay. Suppose this is an intrinsic semiconductor. Silicon, germanium, whatever you choose, whatever you say. So if this is the top of the valence band, and if this is the bottom of the conduction band, the Fermi level lies exactly in the middle. So if the T temperature is greater than 0, so electrons will be moving from here to there. Suppose electrons have reached here, so correspondingly equal number of holes will be there. So electron concentration of electron and concentration of electron and concentration of hole are equal. They are present in equal numbers in intrinsic semiconductor. Okay. Now, if I consider suppose I dope it, okay, do N-type doping or whatever you do, it's a P-type doping. P-type doping means you are adding one acceptor like aluminium, which will be accepting the electron. So what would happen? So now electron will be accepted, okay? So who will be accepting the electron? You need a donor level, okay? So this is going to be the donor level, sorry, acceptor level, which is coming from the P side. And obviously this is going to be close to the valence band, top of the valence band. This is the top of valence band. This is the bottom of conduction band. Energy gap between them is a band gap, G. Okay. So now this is the Fermi level is common, very common. Okay, so this is the now this is the bottom of the conduction band. So obviously now this was the initial Fermi level. Now electrons, this is it electron can stay here also because accepted. So holes can be coming here. Okay. Accepted level is there, aluminum. Now what would happen? So this is P-type. Now suppose I consider one N-type semiconductor. N-type semiconductor means N-type means donut type. Okay. So electron will be donated. So this is donor level. So Fermi level will be close to the conduction level. So this is in the bottom of the conduction band. And this is your top of the valence band. You see, A beautiful picture is coming now. So now this is your top of the bottom of the conduction band, and this is your top of the valence band for the p side. Now this is your bottom of the conduction band for n side. Yes, and this is top of the valence band for the p side. Now suppose you want to join p and n and you want to make a diode. What would happen if you join it? You see it is like this much. You are joining it. So the moment you join p side and n side, you see if you have got an electron here in front of the electron, you are creating a voltage barrier of this much of height. So that means electron can go to the other side from that is from n side to p side if and if it has got more energy than this barrier height. Okay, this barrier height is called barrier potential that is developed at the junction, or it is equivalent. This is called cut. Okay, V0 is the value. Okay, this is V0. E into V0 is equal to the cut-in voltage. That's why if you see, that means if I've got an electron with some amount of energy E here, it cannot automatically go to the other side of the other side. You have to provide it. You see, it cannot go to the other side of the junction automatically. How do you do it? You have to provide energy to this electron so that it can go to the other side. Okay. How do you provide that much of energy? Try to know it. Okay. Now this is obviously what I have done. I have made a PN junction diode. I've joined P side and N side and made a PN junction diode. Popularly, this is symbolized like this way. Okay. P side and N side, they are clubbed together. So normally, try to realize it in a PN diode. If this is your configuration level, okay, acceptor level, valence band, this is the conduction band, bottom of the conduction band, and in the N side, this is the conduction band, donor level. The bottom of top of the valence band. So this is your junction. This junction is the key. PN junction we have created. So if an electron has to go from here, from the conduction band of this side to the other side, it should have more energy than this energy gap. Okay, it should have more energy than this gap. If it is V0, normally if electron is greater is E, it can go to the other side if it has got more energy than V0. But now it don't have more energy. Okay, then now it don't have more energy, so it can't go to the other side. So how do you do? You have to energize it. You have to increase E. How do you do so? In normal diode, that you do by connecting it with a voltage source. Suppose you apply a voltage source V1. If you apply a voltage V1 here, okay, that means you are providing E into V1 amount of energy. You consider to the electron, okay, because electronic charge is minus E, and V1 it is connected to the negative polarity of the battery, the N side. So you are providing this much of energy. So total energy of the electron, the moment you the switch on V1 of the electron, total energy now becomes E plus EV1. Now what you have to do, you can vary this voltage in the diode experiment. So that means you can increase this voltage And if you do so, you can actually increase the total energy of the electron, and you push electron energetically up and up, and making it more and more unable to cross the junction. So if you look at the diode now, try to plot the current through this diode against this voltage V1. Initially, for V1 equal to 0, you get nothing because it does not have enough energy. Now what you are doing, if you keep on increasing the voltage from zero point 0.1 to zero point 0.2 to zero point 0.3, you see what you are doing, you are helping the electron, you are actually making this energetically up and up to move across the junction. So you are increasing its energy, okay, energetically up and up. And you see in a normal diode, nothing happens. The moment, normal germanium diode, unless and until you reach say 0.7 volt or zero point 0.7, that means you are this barrier height is close to this V0 is actually close to 0.67 electron volt. So if you provide energy more than 0.67 electron volt, then and only then electron is, okay, if it is getting more energy than this much, okay, this is V0. If the energy of the electron is more energy than this, or that is that 0.67, then and only then electron, okay, can go to the other side, can cross the junction, and will give you current to the circuit. So the proper idea is that if electron crosses the junction, same thing is for hole, then and only then you get a current. Okay, so the idea is that at 0.7 you get a bit of current. Now in a diode practical, now if you keep on increasing the voltage above 0.7, you see above 0.7 means now total energy, if you look at the total energy expression, E plus E V1, you are now giving, you can 0.7 means you can, whatever be the value of V1 you give, total energy will be more and more, and you are living here every time. So electron can always go to the other side in large number because now it has got more energy. So suddenly you see a lot of electrons moving across the junction. The current will grow. So for a small change in voltage, you see a rapid growth in the current through the diode, and that is nonlinearity. Okay, suddenly you see a lot of current. So here diode is off, and here diode is on. So this makes one of the popular application of the device as a switch. Okay, in logic gate design, it is used for preparing switch. Now this is the forward bias characteristic of a junction diode. If you try to see what happens in reverse bias, same story will happen. Reverse bias diode characteristic is like this much. P-N junction diode. Again, okay, again this is the Fermi level. Okay, this is the acceptor, so valence band, top of the valence band, bottom of the conduction band. This is P side. From the inside, okay, this is the top of, this is the conduction band, this is the donor level, so valence band. These are the, this is the junction you're creating. Okay, now an electron wishes to go from this side to this side. It can only go if the energy is greater than V0. So what you have been doing so far, you are trying to increase the total energy by adding, by applying forward bias. Okay, now what I shall do now, I was applying a voltage here, say like V1. So I was increasing V1, more and more energy. V1 is more and more, it was moving up in energy. So ultimately it has crossed the junction. Okay, now I'll talk about reverse bias condition. Reverse bias diode means this is this circuit. Now reverse bias means if you apply voltage V1 here, now the energy that will be experienced by an electron is minus E into plus V1, because now it is connected with positive polarity of the battery. So if you look at this formula, now it will be modified to E minus EV1. So more and more voltage you apply, you are actually reducing the electron energy more and more. So you are actually reducing electron energy if you increase the voltage V1. So what you are doing, you are not helping the electron. You are actually lessening the electron energy. You are making the reducing the electron energy and making it less and less probable to cross the junction. So it can't go. So that's why if you look at the diode graph, now you are working, you are increasing V1 to the other side, but that means you are not helping the electron, you are lowering its energy. So that means electron cannot go to the other side. Okay. Then how do you get the current? Obviously, don't get any appreciable current. You can get a very small amount of current for the electrons living in the minority electron in the p side. Okay, because you see, they are already at the higher energy level, so they can always fall down. Okay, but their number is less, so you get a very small current. The mild reverse saturation current, it is, we call it. Okay, very small current flows to the device. Okay, this is called IS, that flows to the device. The value is like I0 exponential minus band gap by eta kt. Now this is thermal current. Okay, this is the temperature dependent current that will flow through the device. Okay, that is always present. Is very low microampere, and the normal diode current, which is above zero point 0.7 volt or so, this is of the order of milliampere. So you can see one of the application of the diode. Obviously, it can be used as a switch. Okay, above zero point 0.7 volt is on, otherwise it is off, or to be used as a voltage rectifier. So it can be current rectifier. That means you see in forward bias, you see it is on, in reverse bias it is off. So it can be acting as a valve. Okay, so these are the major application of the diodes. Now with all these things in mind, let me get back to the PowerPoint a bit. You see, whatever I told you, you see it is happening. So electron and holes are coming, recombining. This region, just come back to the picture. This region just formed now. This region is called depletion region. This is the depletion region, junction where potential variance is created. Okay, this is the junction or depletion region. It is depleted of free charges, depletion. No free charges exist there. Okay. Now it's, you see how it is actually forming the depletion region. You can see this is the depletion region formed. So this is how it looks like as I've shown you. I have shown you possibly better picture. Now you see the forward bias case as I have presented in front of you. You see electrons, you see forward bias case, you see the pictures. There is a depletion region formed. Now forward bias means, you may think in this way also, that is the other way to look around. You see from this picture, from this side you can see electrons have negative charge connected with negative polarity, so they are pushed in inside the device and they are crossing the junction. If they have got more energy, obviously, as I have shown you earlier, so they will cross the junction and you will get the current. So they are crossing the junction and you are getting the current. You see, just to see, you see they are pushed in, the electrons are crossing the junction and you are getting the current. Okay. They are pushed in, you see, they are actually pushed in here and you get current. You get the current, you see, they're pushed in, just electrons are pushed in across the junction and you're getting the current. Okay, that is another way to look into this situation. So in forward bias, an extra battery is applied, as I showed you. The electrons are pushed in. This is another way to look into this whole situation, as I've shown you, but I have possibly shown you a better way to how you energize the electron to cross the junction. Okay, so this is another way to look at the whole situation, that you push the electron. Okay, you apply the voltage means you're pushing the electron with the negative polarity, because currently the negative polarity of the battery, negative charge, so they're pushed across junction, you get some current. Okay, some similar points are there. Okay, now reverse bias condition, same story. Okay, reverse bias, as I mentioned few minutes back, the reverse saturation current, you see, reverse saturation for the reverse bias, you see another approach I will be showing you. But in reverse bias, that current is very low. Okay, called reverse saturation current, microampere current. You see the look at the picture. You may think in this way, electrons are having positive charge, negative charge, though electrons are with minus charge. It's another way to look into this. Minus charge connected with positive polarity will be pulled out. Similarly for holes also connected with negative polarity, they are being pulled out. So basically, the depletion rate will be more, it will be widened. So probability of the electron crossing the junction and coming to this side is becoming very less. So for the majority current flow is becoming very less. But I have shown you a better picture. Okay, you see, this is a situation. Okay, you see, it is getting widened. It is getting widened. The moment it is connected, it is widened, and probability of electron going to the other side is very less. So current will fall down. Okay. Now this is a better picture I have shown you. Okay. You see the I have drawn the graphs. Now this is another picture. Okay. Depletion region. You see the electrons are trying to move, but one person is creating the trouble. Coulomb. Okay. Electron has got minus charge. This negative ion on the depletion region will create Coulombic repulsion, a voltage barrier in front of the electron. Electron cannot go. Okay, and to make it go, you have to apply a bias. Okay, then and only then it will go to the other side. Okay, otherwise it cannot go, as I mentioned. Otherwise, it cannot go to the other side. Okay, understand? Now you see the same picture. You apply a bias. Now it can go. Okay, I've already shown you. Now it can go. We're making it. Look at the picture. You're making it energetically more up and making it able to cross a junction. And you get this beautiful picture of the dark characteristic graph of on device. And reverse bias, you see what is happening. Again, Coulombic repulsion is there, but you see, you're not helping the electron. Okay, you're reducing the energy of the electron. So current is mainly the thermal current or reverse saturation current, very low current. Okay. In second year, we'll learn about a particular. We'll apply quantum mechanics to this problem, and I'll get some beautiful results from you. That will tell you even under the cut-in voltage, or even below V0 also, you will get some current. But not because of this approach, some other approach. Okay. So now that is now the concept of breakdown comes into picture. If you apply very high reverse bias voltage, then electron might rupture the bond, okay, and become free because of the strong enough voltage. Okay. For normal diodes, some of the diodes are there like minus 5.8 electron volt is the energy unit. With that, it will rupture the bond, and suddenly you get a lot of electrons coming out, a lot of current you will get. This is called breakdown in a diode. Okay, this is the expression of the reverse diode current. I0 is a reverse saturation current. Okay, expression of the diode current in the reverse bias. Okay, Okay, I've drawn it few minutes back, where it is the voltage equivalent to the temperature, Eg by eta kt. Okay, V is the applied voltage, and you can see that delta V by delta I is the resistance, forward bias resistance, reverse bias resistance, all these things are defined. Dynamic resistance is there, delta V by delta I, which is positive. Positive means positive resistance means decay of the current, and reverse bias also. Okay, it is there, it implies decay of the current. Actually, if you use quantum mechanics, then resistance will become negative. That means that will tell you current can be produced also. Those things will come. Now, the diodes can be used for a variety of purpose. Diodes may be rectifier diode. Okay, as I mentioned, in forward bias resolve, reverse bias resolve, there is a valve which is used for the AC to DC conversion. Signal diodes are there, that is detection of in FMM, in analog communication, in amplitude and frequency modulation receiver. Zener diode acts as a voltage regulator. Vector diode acts for the tuning, okay, for the parallel resonance circuit, tuning the capacitor, okay. Light emitting diode emits light. Photodiode interacts with the lights and gives responses. Tunnel diode gives AC signal, high frequencies. Microwave AC signal. GaN diode also could do the same thing. Schottky diode is metal insulator junction. Metal semiconductor junction for high-speed logic circuit it is used. These are variety of diodes. So you can see here how they look like. Okay. One and these are some of the diode series. One N series, single junction device. Two N series, two junction devices such as transistors. Transistor is a different story, not included in our course here in electronics classes. Electronics industry. Okay. Second standard is there also. For germanium, B for silicon, C for gallium. Okay, gallium arsenide, superconductor. R is also there, like gallium sulfide is the 2,4 semiconductor. Okay, some more points are there related to diodes, device type and function. A for diode, B for character diode, C for F, flow audio frequency flow power transmitter, D for audio frequency flow power transistor, sorry. D for A for radio frequency power transistor, E for tunnel diode, F for high frequency low power transistor, L for high frequency power transistor, S for switching transistor. These are all junctions, PN junctions only. A variety of applications are there. Power devices, Z for Zener diode. Okay, a lot of applications are there. Okay, diode just a junction, a lot of application. And in a diode, the tolerance is there. This code is used like SC1428. SC means germanium. A for germanium. It is used for audio frequency power transistor. Okay. BC149 is very popular silicon audio frequency low power transistor. BY114 silicon crystal diodes. BZC silicon Zener diode. 6.3 means it will produce 6.3 volt voltage regulator. VY127 silicon rectifier diode. Okay, lead identification is also there. Commonly, cathode is behind the band. Okay, left hand side is P side, right hand side is. Okay, very popular symbols are these. This is P side. This is N side like this. Peak inverse voltage is written there. Maximum voltage diode can survive under reverse bias. Above that, it will destroy. Maximum forward bias current also is written. Reverse saturation current is also written. Okay. Maximum power transfer that is dispatched in the diode. Operating temperature is also mentioned. All these are features. Now, rectification application of the diodes as rectifier over high voltage protection circuits, limit a clamping voltage doubler circuit as compensator and logic gates. Okay, as I mentioned, a switch. One of the popular application of the diode is a Zener diode. Okay, next video lecture I'll talk about Zener diodes. Thanks for the time.